Hello students, this is Dr. John, your physics and math professor. Today we're going to unravel the mystery of gravity, especially when it deals with something like a satellite. This could be a satellite orbiting the Earth, or the moon orbiting the Earth, or the Earth orbiting the sun, or anything like that as well. The principles will be the same that apply to this. We're going to try to find the total energy of the system, of the orbit of this thing here. We'll start with finding the kinetic energy and then the potential energy, because of course the total energy is going to be equal to the energy kinetic plus the energy potential. So once we find this and this, we just add them up and we find the total energy of orbit. And then we're going to find the escape velocity as well. We're going to start with the easy one, that is the kinetic energy. And here we have a quick diagram of this. I've drawn the Earth in the center and here the satellite, and it's orbiting around like this with a velocity and a radius of curvature. And if you remember from your other problems that you did, the force that needs to be pulling this toward the inside, which causes the inward acceleration and keeps changing the velocity, is going to be equal to m v squared over r. I've just got too many things in the way here. Let me erase a couple of these things. So that's the force that's going to have to be pulling toward the center constantly to continue to make it go around the circle. But of course, this is just the force that you're going to need. This doesn't tell you the cause of the force. There has to be another cause for centripetal or centripetal force or centripetal acceleration toward the center. In this case, that's gravity. As simple as this, the force of gravity is equal to big G, the gravitational constant, times m. In this case, that's the mass of the Earth. I'm using big M for that. Little m for the satellite divided by r squared. We're always measuring to the center of the Earth. From the center to the center of the satellite to the center of the Earth is our r. Don't go to the surface of the Earth. You're going to get a wrong answer. So this is going to be the cause of the centripetal force. So that means this here has to equal this here. So I'm going to erase some of this so I can write those things out there and do the calculation for you. So here I have the force of gravity. The standard gravity formula, which I have right here, is equal to the centripetal force, which I have right here. I don't need this. And of course, if you notice here, there's an m here, a little m, which is the mass of the satellite. And since those are the same on both sides, we can eliminate those. And notice there's an r here and an r here, so we can multiply through by r, cancel one of the r's, and we're left simply with this. V squared is equal to this. So I'm going to write that over here. I'm going to erase some of these things. We don't need them right now. So here I've written this down here, just so we have it for a reference. And if we want the kinetic energy, remember the kinetic energy for anything that's moving is just equal to 1/2 mv squared. This little m here is dealing with this m, and we already have v squared right here. So let's multiply that by little m. So we're going to have g big M little m, that's this one here, over r, and then divided by 1/2. So I can put a 2 down there like that. So this would be the kinetic energy. Notice this is very similar to the force of gravity, only that would be an r squared, and there's a 2 down there. So let me write this down there as well. We're going to need that as well for later. So I wrote this down here as I promised. I also wrote it up here because that's one of the things we want to do. Now the next thing we want to do is we want to find out the potential energy. To do that, I'm going to erase a couple of things here and just think about this for a second. If you remember how you calculated potential energy, if you had, let's say you had this box and you were on the ground floor here and you wanted to lift it onto a table. So you took this box, lifted it onto the table. Remember, the potential energy of the box changed. The potential energy of the box in this case would be mgh, if this is the mass of the box, and this is the height that you lifted up, like that. So this here is just simply this. What we have is the formula where you would get the work that you would do would be equal to the force you applied times the distance that you apply that force. In this case, to lift this box, let's say you're lifting it at a constant velocity, you're just grabbing the box and lifting it up, then your upward force is going to have to be the same as the gravity force of this thing. The gravity force of this thing, of course, is mg. So that means your upward force is going to have to be mg to balance that, and you're going to have to push that force over a distance d. So the work you're going to do is do the force times the distance. I'm just going to write that down here. Now I've got this written over here. The work is equal to the force times the distance. And for the potential energy of a box, it's just mgh. Now in this case, what we have determined here, or what we've decided ahead of time, is that this level here, the level where you're on the ground level or on the floor, is your zero potential energy. And this is just simply the change in potential energy. So we should really call this delta PE. So the change in potential energy is going to be equal to the work that you do to get it there, from here to here. And this here is a positive work because you're pushing in the same direction as your vector movement of h, because h moves upward and you're pushing it, your force is upward. So that's a positive work. Hence, there's a positive change in potential energy. I just erased this here for a second. Now for the potential energy of the satellite, we're going to apply the same principle. But one of the big problems we have is we don't know, what do we call the zero? What do we call the base for the potential energy? Calling the potential energy zero, then the potential energy would be something over here. Let's think about this for a second. A couple of different options we would have. If this is the satellite here, there we go, fancy Star Wars satellite, and it's orbiting like this. What would be the potential energy of the satellite? This is the Earth. So one option for potential energy being zero would be the center of the Earth. That's a very natural, normal idea. And then what you have to do is you have to push outward with your force to move it in this direction. Now, of course, the problem is, as you're going outward, notice the tiny little circle I have there, it's going to have a certain mass inside. And the force of gravity that you have, which I erased that formula, like that, the force of gravity right there is big G, gravitational constant, m of the Earth over m of the satellite over r squared. This r squared, of course, would be the distance to the center. M is the mass of the satellite. It doesn't change. But notice here, if you were saying, starting with that little circle over there and pushing outward with your force is pushing outward like that, you're going to have the mass that's inside that little circle there, right there, is going to be changing constantly. So as you're moving outward, the mass is going to get bigger because you're now going to be including all of this mass. So what you're going to be doing as you're pushing outward, you're going to have to constantly change the mass that's inside the circle right here, plus you're going to have to change the radius. This is a very complicated calculation to figure out the work done to getting from the center to here. So for most high school students, that would be a pretty complicated problem. Well, let's say you started instead on the surface of the Earth right here. Let's say we started right here. We're going to start as this. Well, you're still going to have to, as you move the satellite outward, you're going to have to call this your zero energy. But then inside the Earth, let's say you're moving slightly inward, or let's say you're doing something unusual and you're calling this, maybe it's a gaseous cloud or something, a gaseous planet, and you're moving inward from that, you're going to have a negative potential energy there and a positive potential energy there. Whatever you choose is going to be very complicated. So what instead, we've sort of flipped something around. And instead of calling the zero energy there, what we've said is, let's call the zero energy far away. Let's go as far away as possible so that we have basically, we're completely escaped the planet, and we will call that our zero potential energy. Then as you move closer to the planet, notice what happens. If you take the satellite now and you're moving it closer to the planet, I'm moving the satellite closer to the planet, I'm going to have to apply force in this direction because it's going to want to fall into the planet. And the dr, or the radius, this is the force that's applied. This is the radius. The radius is outward, the force is outward, but it's going to move in the opposite direction of the force. So the work I'm going to be doing here is going to be negative. So the potential energy that's going to, if I call the zero at infinity out there, then as I move closer, I'm going to have a more and more negative potential energy. How do I calculate that? Well, the way that I calculate that is I erase this first. So the work that I'm going to do is going to be the force times the distance. And the force is going to be this thing, GMm over r squared. Gravitational force is this way, but I'm going to have to push this way. But the r vector is going to have to be out this way as well. So dr is going to be in this direction, and the force I have to apply is going to have to be positive to keep this thing from falling inward. So this is going to be the force, but I'm going to have to integrate this. So for those of you who are familiar with integration, that's quite fine. Integration just means you're adding up everything. So here, if you have a curve like this, integration means adding up all the area underneath this curve. So if the curve is constantly changing, you're going to have to create tiny little intervals where you're adding up those sort of rectangles there. And that's what integration does for you. I will not try to explain integration for you, but the integration is going to be, we're starting over there at infinity. So we're starting at infinity, and we're going to integrate all the way down to r, all the way from infinity to this distance r. How do we do this? Well, we take the integral of this, and that's going to be equal to negative GMm over r. And we evaluate it at r and at infinity. And if we want to evaluate this at r, you just take this r and plug this in here. You're going to get minus GMm over r. And evaluating this at infinity, we're going to have to go minus we have a minus sign here, so that's double minus. So it's minus minus GMm over infinity. This is going to become 0. So this term here at infinity becomes 0 as we want it to. And this is going to be now the potential energy. So let me write that up here. Now some of you may be familiar with differentiation, but not with integration, especially in grade 12. So let me just illustrate this for you really quickly. The differentiation and integration, they're the opposite functions of each other. So it's like x squared and root of x. One undoes the other. So let's just take a look at this, which is what we got for our potential energy, and differentiate it, which would be undoing the integration that we just did. Differentiating this, we're going to have minus GMm. Those are going to be a constants. This is r to the minus 1. Remember the derivative of that? Take down the minus 1. So you're going to have minus r to the minus 2 and reduce this by 1. So this is going to be this over r squared. But because we're taking down the minus 1, it's going to make that plus. So this is GMm over r squared. So if you take this, which is your potential energy calculation, and differentiate it, you're going to get back your force of gravity. Because remember, we took the integral of this to get this. So hopefully that helps you to understand that a little bit. And now we have a calculation for the potential energy of that point if our potential energy is 0 at infinity. So we have a couple of more things that I want to do. One is we want to find the total energy of this satellite in the orbit. That's going to be the combination of the kinetic energy and the potential energy. So I just wrote this over here. I took the 1/2 out. I took that 1/2 out of there so you can see it. So all of this is the same. This is minus this. So if you take this minus this is 2/2. So the total energy is going to be minus 1/2 GMm over 2r. Only minus. That's the total energy because this is 2/2 and there's a 1/2 over here. So it's minus this, which looks exactly like the kinetic energy, only it's negative. So let me write that down here for you. Okay, I wrote the total energy over here. Remember, it looks exactly like the kinetic energy, only it's negative. So let me just sketch these for you here really quickly, and I'll try to do those color-coded. So here's the kinetic energy. It's positive. So it's going to be, obviously, as we go to 0r, it's going to go to infinity, and then it's going to do something like this. As we go to infinite r, it's going to go to 0. And then we have the purple one here, and it's going to be twice as big as this, but negative. So instead of this here over here, it'll be something like this. I'm exaggerating a little bit. So this here is going to be the potential energy. This one here is going to be the kinetic energy. And let me find a whole different color to draw the total energy. Well, if you add this up, this total energy here is going to look exactly like the kinetic energy, but just reflected over the x-axis. So it's going to be just like this. There, this is the energy total. So this is a graph that you have. Now you might say, well, what if we go right to the center of the planet? Obviously, that's not something that we're ever going to do. Just think of it this way. If you drew a line like right here, this might be the surface of the planet. This might be your orbit. There you go. So this is sort of like a view here right on the Earth, where this might be the surface of the Earth right here. And this might be the orbit over here. So these are the areas that you're actually going to use. So this is a graph that you're going to see. I'm going to try to make a study sheet for this as well, so you can download it on physicsdoctor.com. Hopefully you find that very useful. Now there's one more thing that we wanted to do, and that we wanted to find the escape velocity. The escape velocity really, in a sense, is very simple. What you do is you say, what is the potential energy of the satellite at a certain place? Well, that is this right here. So the potential energy is this. It's minus GMm over r. That's the potential energy. And if you want to get this escaping all the way to infinity out here, we're going to have to add enough energy. So we're going to have to add plus 1/2 mv squared. We're going to have to add enough energy here to make this equal to 0. Or this energy is going to have to be equal to this one, because we just take this to the other side and make it positive. So this here, I can erase that and make this an equal sign. So I'll just make that an equal sign. And again, if we're doing this calculation, the little m cancels. The 2 can go to this side like this. And we're having v squared like that. So let's write that out. V squared, or if I take the square root, 2gm over r. So this would be the escape velocity that we would need. Let me write that in here. If you have a satellite in this orbit, add this, give it this velocity, and you're going to escape out from the planet's grip altogether. Well, I hope that helped. I hope that helped to detangle and make clear a lot of this gravitational stuff, especially when it came to satellites and orbits and stuff like that. These formulas and this construction here will help you a lot. If it did, like and subscribe, and I will see you in the next video. Bye-bye.